3.10. Let a sub n be a sequence of positive terms such that the limit of a sub n plus 1 over a sub n is equal to L, and then apply Solt's theorem to calculate this limit. Okay, so this is the same as the limit when n goes to infinity of a sub n to the n divided by a sub n, a sub 2, a sub n, all of them to 1 over n squared. Okay, so if we call that this limit L, for instance, in order to deal with this and this exponent that I don't really like, what I'm gonna do is, we've done before, calculate the logarithm of L, and the logarithm of L is 1 over n squared, the logarithm of this a sub n, and then a sub 1, a sub 2, blah blah blah, a sub n. Okay, now I can use the properties of the logarithm to do this. This is the same as the logarithm of this minus the logarithm of this. Okay, and the logarithm of a sub n to the n is n times the logarithm of a sub n, and then minus, and then it's the logarithm of a sub 1, a sub n, but this, as the logarithm of the product, is the same as this sum of the logarithms. Okay, now we don't know what this is going to happen with the numerator. Sorry, yeah, this is limit when n goes to infinity and the limit when n goes to infinity. Sorry about that. But the denominator is going monotonically increasing to infinity. Okay, so we can apply Stolz theorem, as they say. They ask us to do Stolz theorem, and let's see what happens. Okay, now we have n logarithm of a sub n minus the sum from k equals 1 to n, the logarithm of a sub k, minus, and then it's n minus 1 logarithm of a sub n minus 1 plus the sum from k equals 1 to n minus 1 of the logarithm of a sub k, and then n squared minus n minus 1 squared, but we know this is going to be 2n minus 1. We have done this before. Okay, so now we have the limit when n goes to infinity, and so then we have the logarithm n. We can write this like n logarithm of n a sub n minus 1 minus the logarithm of a sub n minus 1, right? Well, no, forget I said anything. Forget this. Sorry about that. This is the logarithm of a sub n and n plus. Okay, so, and as usual, we have, this is the sum from k equals 1 to n of the logarithm of a sub k, and this is the sum of k equals 1 to n minus 1 of the logarithm of a sub k. So if you take the sum and subtract this sum, as you can see, every term in the sum appears here except the last one. So we have n logarithm of a sub n minus the logarithm of a sub n, that results from this taking from this sum, subtracting this sum, and then minus n minus 1 logarithm of n minus 1 divided by 2n minus 1. Okay, this is n minus 1 times logarithm of a sub n, and this is n minus 1 logarithm of a sub n minus 1. So this is n minus 1 times the logarithm of this minus the logarithm of this, but because of the properties of the logarithm, we can write it like this. This is 2n minus 1. And so now we have the limit of the product, the limit of this and the limit of this. Okay, so the limit of this is going to be 1/2. Okay, and the limit of this is going to be the logarithm of this L. Okay, so the limit of a sub n over a sub n minus 1 or a sub n plus 1 over a sub n, it doesn't matter. It's the logarithm of L. So the result is 1/2 of the logarithm of L, or if you want, the logarithm of the square root of L. So the logarithm of capital L, capital limit, is the logarithm of the square root of L. So the limit that we want is the square root